Dear students, in this video I am going to explain chapter 10 of your module 4, that is file system interface. Actually it is a part of storage management. Since main memory is usually too small to accommodate all the data and programs permanently, the computer system must provide secondary storage to back up main memory. Modern computer systems use disk as the primary online storage medium for information, that is, programs and data. The file system provides the mechanism for online storage of and access to both data and programs residing on the disk. A file is nothing but a collection of related information defined by its creator. The files are mapped by the operating system onto physical devices. Files are normally organized into directories for ease of use. For most users, the file system is the most visible aspect of an operating system. It provides the mechanism for online storage of and access to both data and programs of the operating system and all the users of the operating system. The file system consists of two distinct parts, that is, a collection of files, each storing related data, and a directory structure which organizes and provides information about all files in the system. File systems live on devices which we described in the previous chapter and will continue to discuss in the following one. In this chapter, we consider the various aspects of files and the major directory structures. We also discuss the semantics of sharing files among multiple processors, users, and computers. Finally, we discuss the ways to handle file protection necessary when we have multiple users and we want to control who may access files and how files may be accessed. File concept, that is, this particular slide explains the major introduction of the file. Computers can store information on various storage media such as magnetic disk, magnetic tapes, and optical disk. So that the computer system will be convenient to use, the operating system provides a uniform logical view of stored information. The operating system abstracts from the physical properties of its storage devices to define a logical unit, that is, file. Files are mapped by the operating system onto physical devices. These storage devices are usually non-volatile, so the contents are persistent between system reboots. Then let us discuss what is file. A file is the collection of related information that is recorded on the secondary storage. From a user's perspective, a file is the smallest allotment of the logical secondary storage. That is, data cannot be written to secondary storage unless they are within a file. Commonly, files represents programs and data. Data files may be numeric, alphabetic, alphanumeric, or binary. Binary in the sense the file may contain only the binary data, that is 0 or 1. Numeric, numbers. Alphabetic, that is alphabets A to Z. Alphanumeric means numbers as well as alphabets. So files may be free form or such as text files, or they may be formatted rigidly. In general, a file is a sequence of bits, bytes, lines, or records, the meaning of which is defined by the file's creator and user. The information in a file is defined by its creator. Many different types of information may be stored in a file. That is, source or executable programs, numeric or text or photos, music, video, and so on. A file has a certain defined structure which depends on its type. A text file is a sequence of characters organized into lines. A source file is a sequence of functions, each of which is further organized as declarations followed by executable statements. An executable file is a series of code sections that the loader can bring into memory and execute. Next we discuss about attributes. What are the different attributes or the properties of a file? A file is named for the convenience of its users and is referred to by its name. A name is usually a string of characters such as example.c or program.c. Some systems differentiate between uppercase and lowercase characters in the names, whereas other systems do not. When a file is named, it becomes independent of the process, the user, and even the system that created it. For example, one user might create the file example.c and another user might edit that file by specifying its name. The file's owner might write the file to a USB disk, send it to an email attachment, or copy it across a network, and it could still be called example.c on the destination system. Now let us see what are the different attributes. First one is name. It is the symbolic name, that is the only information kept in the human readable form. Second one is identifier. This unique tag, usually a number, identifies the file within the file system. It is the non-human readable name for the file. Third one is type. This information is needed for systems that support different types of files. Next is location. This information is a pointer to a device and to the location of the file on the device. That is, this attribute defines where the file is located. Next one is size. The current size of the file may be in bytes or words or blocks, and possibly the maximum allowed size are included in this attribute. Next one is protection. Access control information determines who can do reading, writing, executing, and so on. Last one is time, date, and user identification. This information may be kept for creation or last modification and last use. This data can be useful for protection, security, and usage monitoring. Next, let us study about what are all the operations that can be done on the file. A file is an abstract data type, as we all know. To define a file properly, we need to consider the operations that can be performed on files. The operating system can provide system calls to create, write, read, reposition, delete, and truncate the files. Let us examine what the operating system must do to perform each of these 6 basic file operations. These are called as basic operations. It should then be easy to see how other similar operations such as renaming a file can be implemented. So first one is creating a file. It is a two-step process. First, the space in the file system must be found for the file. Okay, first space must be found. Second, the entry for the new file must be made in the directory. Okay, that's about creating the file. Next is writing a file. How to write the content to the file? To write to a file, we make a system call specifying both the name of the file and the information to be written to the file. Okay, name of the file and the information. Given the name of the file, the system searches a directory to find the file's location. The system must keep a write pointer to the location in the file where the next write is to take place. The write pointer must be updated whenever a write occurs. That is about writing a file. Next, reading a file, in sense how to read data from the file. To read from the file, we use a system call that specifies the name of the file and where the next block of the file should be put. Again, the directory is searched for the associated entry and the system needs to keep a read pointer to the location in the file where the next read is to take place. Once the read has taken place, the read pointer is updated. Because a process is usually either reading from or writing to a file, the current operation location can be kept as a per process current file position pointer. Both the read and write operations use the same pointer, saving space and reducing system complexity. So the important thing here is how to keep track of per process current file position pointer. Next is repositioning within a file. The directory is searched for the appropriate entry and the current file position pointer is repositioned to a given value. Repositioning within a file need not involve any actual input-output. This file operation is also known as a file seek. Next is deleting a file. To delete a file, we search the directory for the named file. Having found the associated directory entry, we release all file space so that it can be reused by other files and erase the directory entry. Last one is truncating a file. The user may want to erase the contents of a file but keep its attributes. Rather than forcing the user to delete all the file and then recreate it, this function allows all attributes to remain unchanged except for file length, but lets the file be reset to length 0 and its file space released. These 6 basic operations comprise the minimal set of required file operations. Other common operations include appending new information to the end of the existing file and renaming an existing file. These primitive operations can then be combined to perform other file operations. For example, we can create a copy of a file or copy the file to another I/O device such as printer or a display by creating a new file and then reading from the old and writing to the new. Sometimes we may also want to have operations that allow a user to get and set the various attributes of a file. For example, we may want to have operations that allow a user to determine the status of a file, such as the file's length, and to set the file attributes, such as the file's owner. Most of the file operations mentioned involve searching the directory for the entry associated with the named file. To avoid this constant searching, many systems require that an open system call can be made before a file is first used. This is called as open file table, containing information about all the open files. When a file operation is requested, the file is specified via an index into this table, so no searching is required. When the file is no longer being actively used, it is closed by the process and the operating system removes its entry from the open file table. Create and delete are the system calls that work with closed rather than open files. This is about open files. So in this particular figure, you can see different file types, name and extension. For example, an executable file, its extension can be .exe, .com, .bin or no extension. Its function is ready to run machine language program. Likewise, we have object files with the extension .abj or .o, source code .c, .ccc, .java, etc. Batch file .bat or .sh, markup files .xml, .html, etc. Word processor, our XML file or RTF or docx word file, etc. Library file .lib, print or review, GIF, PDF, etc. Archive file .rar, .zip, .tar, etc. These are the multimedia files like .mpeg, .mov, .mp3, mp4, etc. Different files, their extension and the functions. Let us study about access methods. Access methods in the sense how to access the file. Files store information as we know. When it is used, this information must be accessed and read into computer memory. The information in the file can be accessed in several ways. Some systems provide only one access method for files. So first one, let us discuss about sequential access. It is the simplest access method which is called as sequential. Information in the file is processed in order, one record after the other. This mode of access is by far the most common. For example, editors and compilers usually access files in this fashion. Here, read operation, which is called as read next, read the next portion of the file and automatically advances the file pointer. Similarly, write operation called as write next appends to the end of the file and advances to the end of the newly written material. Consider this figure. There is a beginning of the file and end of the file. Suppose this is the current position, then read or write takes place from left to right, whereas rewind can take place from the current position towards left, beginning of the file. Next method is direct access. Here, a file is made up of fixed length logical records that allow programs to read and write records rapidly in no particular order. The direct access method is based on a disk model of a file, since disk allow random access to any file block. For direct access, the file is viewed as numbered sequence of blocks or the records. Thus, we may read block number 14, then read block number 53, and then write to block number 7. See here, there are no restriction on the order of reading or writing for a direct access file. For the direct access method, the file operation must be modified to include the block number as a parameter. Thus, we have read n, where n is the block number, and write n rather than using write next. So, consider this code. Sequential access reset can be implemented with the help of direct access like this. CP is for current position. Current position is equal to 0. Reset means setting the value to 0, no? So reset is implemented by current position is equal to 0. Read next can be implemented like this. First read the current position pointer CP and then it is incremented by 1. Similarly, write next. First acquire or get the current position. So write to the current position and then it is incremented by 1. This is about direct access. We also have other access methods. They can be built on the top of a direct access method. That is, generally they will make use of direct or sequential access only. These methods are generally involve construction of an index for the file. The index, like an index in the back of a book, contains pointers to the various blocks. Will be easy for searching the contents, isn't it? To find a record in the file, we first search the index and then use the pointer to access the file directly and to find the desired record. For example, you see here, this is the index file and this is the relative file. In the index file, you can see the names, names of the record. They have just given as last name, maybe Adams, Arthur, Asher or Smith. If you want to access the contents related to Smith, you can have it with the help of relative file. There is a pointer like this. Using this pointer, the contents can be accessed with the help of relative file. This relative file means the file where exactly the contents are stored. Index file means which contains just the index. Next we have disk structure. We consider how to store the files now. Certainly, no general purpose computer stores just one file. There are typically thousands, millions, even billions of files within a computer. Files are stored on random access storage devices including hard disk, optical disk and solid state. Partitioning is useful for limiting the size of individual file systems, putting multiple file system types on the same device or leaving part of the device available for other users. File system can be created on the top of these parts of the disk. Any entity containing a file system is generally known as volume. Volume may be a subset of a device or a whole device or multiple devices linked together. Each volume can be thought of as virtual disk. Now consider this figure. There are two partitions A and B. They are stored in a directory structure like this. One directory which contains some files, another directory contains some files. So first part is called as partition A and second part is called partition B. Altogether it is stored in disk 1. Then partition C is here which is stored in disk 2 as well as disk 3. Altogether this is called as partition C. half of partition C can be stored in disk 2 and remaining half can be stored in disk 3. So totally we are using 3 disks, disk 1, disk 2 and disk 3 to store partition A, partition B and partition C. Later they can be linked. Next, directory structure. The directory can be viewed as a symbol table that translates file names into their directory entries. If we take such a view, we see that the directory itself can be organized in many ways. The organization must allow us to insert entries or to delete entries or to search for a named entry or to list all the entries in the directory. In this section, we examine several schemes for defining the logical structure for the directory system. When considering a particular directory structure, we need to keep in mind the operations that are to be performed on a directory. So first one is search for a file. We need to be able to search a directory structure to find the entry for a particular file. Since files have symbolic names and similar names may indicate a relationship among files, we may want to be able to find all files whose names match a particular pattern. Second one is creating a file. New files need to be created and added to the directory. Next is delete a file. When a file is no longer needed, we want to be able to remove it from the directory. Next is list directory. We need to be able to list the files in a directory and the contents of the directory entry for each file in the list. Rename a file. Because it is required because the name of a file represents its contents to its users. We must be able to change the name when the contents or use of the file changes. Renaming a file may also allow its position within the directory structure to be changed. Last one is traverse the file system. We may wish to access every directory and every file within a directory structure. For readability, it is a good idea to save the contents and structure of the entire file system at regular intervals. Often we do this by copying all files to magnetic tape. This technique provides a backup copy in the case of system failure. In addition, if a file is no longer in use, the file can be copied to tape and the disk space of that file released for reuse by another file. So in the next slide, let us discuss different directory structures. First one, we have different types like single level directory, two level directory, tree structure, acyclic graph structure, general graph structure, etc. First one is very simple one called as single level directory. The simplest directory structure is the single level directory. All files are contained in the same directory, which is easy to support and understand. So here you can see, consider this figure. The directory called as cat, bo, a, test, data, etc. will be having some files. Okay, in the single level directory, which has a different directory and different files. But there are some limitations. When the number of files increases or when the system has more than one user. Since all files are in the same directory, they must have unique names. If two users call their data file test.txt, then the unique name rule is violated. For example, in the cat directory, if we have two files, test.txt as well as test.txt, we cannot have like that. Unique name rule is violated. That is the first limitation. And for example, in one programming class, 23 students call the program for their assignment as program.c. Another 11 students call it as assignment.c. Fortunately, most file systems support file names of up to 255 characters, so it is relatively easy to select unique file names. Even a single user on a single level directory may find it difficult to remember the names of all the files. This is the last limitation. It is not uncommon for a user to have hundreds of files on one computer system and an equal number of additional files on another system. Keeping track of so many files is a difficult task. So we'll go for second level directory called as two-level directories. As we have seen, a single directory often leads to confusion of file names among different users. The standard solution is to create a separate directory for each user. So in this figure, you can see directory related to user 1, user 2, user 3 and user 4. User 1 is having some next level directories like cat, bow, a, test. User 2 is having the same directory a and data. It is possible, okay, because user 1 and user 2 is entirely different. User 3 is also having a directory called as a as well as test. User 4 is having x, data and a. So, in the two-level directory structure, each user has its user file directory that is called as UFD. The UFDs have similar structures but each lists only the files of a single user. When a user job starts or a user logs in, the system's master file directory, that is MFD, is searched. The MFD is indexed by the username or account number and each entry points to the UFD for that user. See in this figure, user file direct. This is the master file directory and this is the user file directory. The subdirectory or the user file directory cat is having some files, boy is having some files, a is having some files. Okay, so here in the user 2 subdirectory a also we have some files here, right? So same file, having same file, it is possible for this directory and this directory. That is the advantage of this two level directory over single level directory. That is tree structured directories. Once we have seen how to view a two-level directory as a two-level tree, the natural generalization is to extend the directory structure to a tree of arbitrary height. Here you can have any number of subdirectories. Root is our main directory or root directory. We have three directories here: spell, bin and program. Spell is divided into three more directories where stat and dist are having some files. And remember, this one circle means files and rectangle means directories. Here the one of the directories of this spell mail is having four more subdirectories. Though out of those four subdirectories, the prog, copy and prt are again subdivided into some directories. They are having some files. That is called as tree structured directories. This generalization allows user to create their own subdirectories and to organize their files accordingly. A tree is the most common directory structure. The tree has a root directory and every file in the system has a unique path name. For example, if you want to give a path for this file, it is nothing but root slash spell slash mail slash exp slash file name. A directory contains a set of files or subdirectories. A directory is simply another file but is treated in a special way. All directories have the same internal format. One bit in each directory entry defines the entry as a file, that is 0, or a subdirectory 1. Special system calls are used to create and delete directories. Now regarding path names. Path names can be of two types, absolute and relative. An absolute path name begins at the root and follows a path down to the specified file, giving the directory names on the path. A relative path name defines a path from the current directory. Absolute starts from the root, relative starts from the current directory. Next is acyclic graph directories. Acyclic graph directory means a tree structure without a graph. Consider two programmers. First, let us consider the situation where we require this acyclic graph directories. Consider two programmers who are working on a joint project. The files associated with that project can be stored in a subdirectory, separating them from other projects and files of the two programmers. But since both programmers are equally responsible for the project, both want the subdirectory to be in their own directories. In this situation, the common subdirectory should be shared. A shared directory or the file exists in the file system in two or more places at once. A tree structure prohibits the sharing of the files or the directories. An acyclic graph, that is, a graph with no cycles, allows directories to share subdirectories and files. The same file or subdirectory may be in two different directories. The acyclic graph is a natural generalization of the tree structure directory scheme. See here, in this particular example, dict and spell are the two directories of root. Dict is having subdirectory count, spell is also having subdirectory count. These two subdirectory counts are going to share a common file, this one. This is called as acyclic graph. And one more you can see, word is having subdirectory word, of spell is having list, another directory. This list is also a subdirectory for W. And a file which is a part of list can be accessed through subdirectory words as well as W as well as all. So this is how shared files can be used in acyclic graph directories. But it is important to note that a shared file is not the same as two copies of the file. They are not the copies. With two copies, each programmer can view the copy rather than the original. But if one programmer changes the file, the changes will not appear in the other's copy. With a shared file, only one actual file exists, so any changes made by one person are immediately visible to the other. Sharing is particularly important for subdirectories. A new file created by one person will automatically appear in all the shared subdirectories. Next is general graph directory. A serious problem with using an acyclic graph structure, that is previous one, is ensuring that there are no cycles. If we start with a two-level directory and allow users to create subdirectories, a tree structure directory results. It should be fairly easy to see that simply adding new files and subdirectories to an existing tree structure directory preserves the tree structure nature. However, when we add the links, the tree structure is destroyed, resulting in a simple graph structure. So the primary advantage of this acyclic graph, primary advantages of previous one is the relative simplicity of the algorithms to traverse the graph and to determine when there are no more references to the file. We want to avoid traversing shared sections of an acyclic graph twice, mainly for performance reason. If we have just searched a major shared subdirectory for a particular file without finding it, we want to avoid searching that subdirectory again. The second search would be waste of the time. Here, see how exactly the cycle appears. Book is a subdirectory of Avi, and Avi is subdirectory of a book. So how exactly a cycle? Avi contains a subdirectory book. Book contains a subdirectory Avi. Then this Avi refers to book again. Next, let us discuss about file sharing. File sharing is very desirable for users who want to collaborate and to reduce the effort required to achieve a computing goal. Therefore, user-oriented operating system must accommodate the need to share the files in spite of the inherent difficulties. So, in this section, we examine more aspects of the file sharing. We begin by discussing general issues that arise when multiple users share files. Once multiple users are allowed to share files, the challenging is to extend sharing to multiple file systems, including remote file systems. First, let us discuss about multiple users. When an operating system accommodates multiple users, the issues of file sharing, file naming, and file protection become preeminent. To implement sharing and protection, the system must maintain more file and directory attributes than are needed on a single user system. Most systems have evolved to use concepts of file or directory like owner and the group. Owner is the person who has created the file and group contains many files. Owner is the user who can change the attributes and grant access and who has the most control over the file. Exactly which operations can be executed by group members and other users is defined by the file's owner. He has the control over the file. Owner and the group IDs of a given file or directory are stored within the other file attributes. When a user requests an operation on a file, the user ID can be compared with the owner attribute to determine if the requesting user is the owner of the file. Likewise, the group IDs can be compared. The result indicates which permissions are applicable. The system then applies those permissions to the requested operation and allows or denies it. So, file sharing for remote file system is the second one. With the advent of networks, communication among remote computers become possible. Networking allows the sharing of the resources spread across a campus or even around the world. One obvious resource to share this data is the form of files. Through the evolution of network and file technology, remote file sharing methods have changed. The first implemented method involves manually transferring files between the machines via FTP. FTP means manually transferring the files between the machines. The second major method uses DFS, that is distributed file system, in which remote directories are visible from a local machine. In some ways, the third method, World Wide Web, is a reversion to the first. A browser is needed to gain access to the remote files, and separate operations are used to transfer the files. Increasingly, cloud computing is being used for file sharing as well. FTP is used for both anonymous and authenticated access. Anonymous access allows a user to transfer files without having an account on the remote system. The World Wide Web uses anonymous file exchange almost exclusively. DFS involves a much tighter integration between the machine that is accessing the remote files and the machine providing the files. This integration adds complexity. Third method is client server model. We have discussed about client server model many times in the previous chapters. Remote file systems allow a computer to mount one or more file systems from one or more remote machines. In this case, the machine containing the files is the server and the machine seeking access to the files is the client. The client server relationship is common with the network machines. Generally, the server declares that a resource is available to the clients and specifies exactly which resource and exactly which clients. A server can serve multiple clients and a client can use multiple servers depending upon the implementation details of a given client server facility. Once the remote file system is mounted, file operation requests are sent on behalf of the user across the network to the server via DFS protocol. Typically, a file open request is sent along with the ID of the requesting user. The servers then apply the standard access check to determine if the user has credential to access the file in the mode requested. The last discussion, that is protection. When the information is stored in a computer system, we want to keep it safe from the physical damage and improper access. Reliability is generally provided by the duplicate copies of the file. Many computers have systems programs that automatically copy disk files to tape at regular intervals. To maintain a copy, should a file system be accidentally destroyed, file systems can be damaged by the hardware problems, power failures, head crashes, dirt, temperature extremes, etc. Files may be deleted accidentally. Bugs in the file system software can also cause file contents to be lost. Types of access. First one, read, that is read from the file. Next is write, that is write or rewrite to the file. Then we have execute, load the file into the memory and execute it. Append, access, write the new information at the end of the file. Delete the file and free space for possible reuse. And list is did the name and attributes of the file. So this is about file system as well as end of chapter 11. Thank you guys.